Okay, ready to go? Last class. I should probably give A's to everyone who is here at this point, right? Anyway, so midterm is when? Monday. And it's 8 to 10, so it's a slightly larger chunk of time, right? So which will give you more time to answer the questions. Same room, right? This time we're gonna, in general, same rules as before, but different twists. So we have to, unfortunately, switch to in-paper format for the midterm. Who can guess why? Cheating. So what kind of attack is possible with an electronic version? Anyone? Well, a trivial attack that I figured out that a couple of people in the class just copy pasted each other's answers. So, and apparently, I can watch you guys not looking on YouTube or something like that during the class, but catching copy paste is really hard, right? So, well, that's unfortunate because we'll just print a tiny little pine, which we could use for Christmas or something, right, for this exam. But I don't see a way of defending against a copy paste attack, right? Plus, it will force people to be in person. So anyway, so then in paper, but everything else is the same. So you can use any resources besides, generative AI, asking for help, searching the web for answers. It most likely will not help you much, but it will confuse us as graders. Not confused, but we will be upset, I guess. So that's why. But if you I had those questions during the midterm. Can I quickly Google the definition of an assembly instruction? Yeah, that's allowed. Just better ask me before, but in general, that's fine because I'm not gonna ask you to remember all the assembly language. Any questions?
Do you use paper?
Yeah, you can use, we will print it out and we'll collect the exam. We'll generate assigned seating again, so to make sure that you sit in some random order, stuff like that, right?
So we don't use grayscale this time?
Yeah, I'm not gonna use grayscale. And we'll then scan the exam. We'll check your IDs as well, so bring your ID. So if you forget, don't worry, no need to go back home. We'll figure out your identity if you can show us something online.
But just to confirm, we can still have a left.
Correct, right? So you can look up anything. Okay, good. And just again, my regular story about my lovely dog. So I like the right picture better, right? So, and the reason is not because I'm an angry little person, but just because I just want a complete histogram, right? And you saw it during the midterm, and I know that it's a little upsetting to find yourself somewhere. Where's my hand? Really? Okay. Find yourself somewhere what was our median was probably around something like 60 something, but we curved the exam quite well as well. And we'll curve this one. So don't worry about the grade, right? I like you to be on the right side of this curve, but if you're not, it's fine. The goal is to be maybe above the median, right? Probably it's A anyway. Any questions about this? It will be scaled slightly proportionally, but again, I'm not so super. We'll go through some sample questions today, so you will see. And I actually just published an exam from last year, and we'll specifically solve it today or part of it if we run out of time, right? I understand that the major question is whether you can have access to answers to previous exams. I will try to put as many answers as I can in the period between now and Monday. Question?
You said we should ask.
Yeah, then you will avoid uncomfortable question of me asking what's going on or TAs. Trying to start the welcome thing. Okay, this is, where's my, yuck. Is this working? How come, like, on a day when I need my tablet the most, it refuses to run? What is it we have here? Really? This. Yeah, this works. I also wanted to ask, okay, so this is clear. Finally, like, again, as you saw this year, the class was changed again one more time. So we changed the homeworks quite significantly. I mean, we don't yet whether it was a good idea. It was a good idea in our opinion, right? Obviously, but maybe you say, oh, look, I mean, you obviously you didn't see the previous homeworks, right? But the previous version of the class was using homeworks based on X with 6, right? Which of course gave you more of an X with 6 exposure, which has advantages, right? But on the other hand, maybe less hands-on experience, plus a lot of those homeworks were solved online and it was hard to assign like unique homeworks, right? So this year we said, okay, let's build on this, boot into C infrastructure. And of course, there were like some inconsistencies in how we were like assigning it because it was for the first time and we could not predict the end result. So maybe we will change the, make files and how everything is set up. But in the end, there's three homeworks, boot into C, create 4 homeworks, create memory manager, enable interrupts and enable system calls and launch a process. Those are new, right? And we would like to hear about it, right? So we'd like whether you appreciated this setup or not. And so as a motivational thing, right? So we will give everyone a 1% of total grade, right? So whatever, it's almost like half a homework or something like that, or 1/3 of a homework, if the total participation in this poll reaches 90%. By the time it closes, right? So it's not uncommon. So we did it in the past and it works. So I encourage you to submit your feedback. Okay, so done for now. So let me switch. Okay, what I wanted to do today is the following. I want to first remind you how X with 6 works, or how everything works, right? And then let me maybe create a new file. User Discord. And then we will try to solve the midterm or the final. So the idea which I'm trying to like remind you, and that's kind of what we were learning in this class all the way. So I'm gonna do a recap of how the operating system boots and works all together, right? So again, just a quick reminder. So the way it works is the following. So you have a CPU, right? CPU is attached to a bus, to something what is called a read-only memory, right? Like essentially it's a flash device which you can reprogram, but typically you never do unless you upgrade the BIOS. And some program sits here. This program is called BIOS, right? And so essentially CPU, when you power on the CPU, calls a specific protocol and reads this BIOS from the read-only memory, which sits on your motherboard, into a real DRAM, right? Like again, BIOS runs first, and probably for the sake of it, it doesn't really matter what's going on, right? So only a small percentage of people will ever program at this level. It's very exciting because there's like a ton of security concerns which are unsolved, but it's hard to get a job because no one really wants to invest in this layer. But at the very end of it, BIOS jumps to, let me ask you a question. What is BIOS doing? So how do we initialize the operating system? Who can tell me? What is BIOS doing at the very, very And anyone? Well, say again. No, if you can, if you have an answer. Right. So how does BIOS handles control to the kernel? Let's put it this way. That's what I'm trying to ask. Or if I ask you differently, what is the first instruction which you guys can control as software developers unless you mess with BIOS? You say, okay, one question is something what is inside main. But a lot of stuff is happening before main, right? The bootloader. And so the bootloader sits on disk. And where does it sit on disk? Where? Yeah, so if you represent the disk as a logical space as well, right? The bootloader by convention sits in a sector 0, right? So BIOS specifically reads this from disk, which means that BIOS itself is smart enough to have a disk device driver. It can talk to the disk. In fact, modern BIOSes can talk to the network and do all sorts of tricks, right? But it reads it and it places it in memory. At what address? Who remembers? 7C00, right? So it essentially just loads it here, right? And this is the very first instructions which you can control as a software developer, right? And okay, so it's a very small program, right? So like it's only 512 bytes, not much. But if you carefully write it, so what it will do is that it will again go ahead. Let me change the colors slightly here. It will go ahead and read something from disk, and it will find a kernel here and load it in memory, right? And x86 doesn't load this kernel into the address which sits at 1 megabyte, right? And it will jump to the, like specifically, since again, that's why we were trying to cover everything. So it's an ELF file, right? And it will have an ELF header, right? And an ELF header will have a field which is called entry. And we're carefully compiling the code in such a manner that it will run. And so the entry will be pointing somewhere. There is no like fixed address at which the kernel will start running, but it depends on how you compile it, right? But nevertheless, the compilation will succeed and will put this entry into the ELF header. And this is where exactly the kernel, first instructions of the kernel will start executing, right? So it's not main yet. So we're far from main, right? Because main needs a couple of things. In a minimal thing, since it's written in C, it needs a stack, right? But also, which is not strictly required, but nice to have, we need to set up two things, right? So we need to set up segmentation and paging, and in order to get running inside main, right? And that's very similar to what you've done in your homeworks, right? So you also were booting into main, setting up a page table, setting up segmentation, right? So this makes sense, the story, right? Okay, what happens next? Question.
What's the BIOS will get something from the first section in the disk?
Yeah, from the sector 0, right?
Okay. So
and it will
load this section into the 7C00.
Correct.
So that's by the program inside the BIOS.
No. This is called a bootloader, right? And so we, who typically boot the machine, like in case of x86, it's created by the x86 build system, right? Again, if it's your private machine, you can reinstall the boot sector the way you like. Typically, it's part of the, okay, if I ask you real questions like, how come you never seen the boot sector in your life? Most likely. I saw a bunch when I was your age because it was harder back then. But so boot sector is part of what program on, for example, Linux machines? Do you know? Correct. So it's part of the grub. So when you install grub, Grub will put something in this in a 512, first 512 bytes of the disk. And then since Grub is bigger than 512, it will put itself somewhere next to it. And the file system will only be even further like in a higher addresses on the disk, right? Just because the Grub cannot fit into 512 bytes, it will bootstrap itself in memory, like kind of like a small kernel. And then the Grub will put a menu and you will choose what to do.
So even when we create like distribution drives, we have to be in the first 500 bytes of that.
Right, yeah, typically. So I don't really exactly know how it works on optical drives because it has a slightly different format. But I would guess so, but cannot 100% confirm. But maybe just dump it and see.
Yeah.
It's logical to have it, but maybe, you know, like USB drives have something magical in sector 0 and then have to put it in 1 or something like that. Okay, so we got it. So after that, we say, look, we start like essentially executing this entry of the kernel, and our goal at this point is to establish at least some address space, right? So create a page table, so essentially, and create segmentation, right? And we create two. We create both of them will be with kernel privileges, right? So it will be kernel data, typical name, and kernel code, and they will cover everything from 0 to 4 GBs because we like don't care about protection anymore, or not anymore, but at this point, right? And then we say, look, and we will create a very simple page table. And x86 uses this boot time page table, which maps only 2 regions of memory, right? So from 0 to 4 megabytes, and then nothing is mapped forever until it reaches 2 gigabytes and 2 gigabytes plus 4 megabytes, right? It's a 4 megabyte per page table, meaning that it has only one level, right? And the pages are 4 megabytes long, and it only has 2 entries, like entry number 0 in a page table and entry number 512, right? And nothing else is mapped, right? And that's enough to enable paging, because why? Because the kernel sits right here at the first megabyte, and that was megabyte. Just erase it. And somewhere at the symbol end, again, similar to how we did it in our homework, right? And who can tell me why is that we're doing this 2 regions, this and this one? And coincidentally, they both map, if we remember, let me just slightly, they both map the same physical memory. So they both map, let's imagine this is 4 megabyte here in physical memory. They both map the same region of physical memory. So why are we doing this? Who can remember?
To avoid page fault.
To avoid a page fault when? Right. So essentially, because when you reload the control register saying I enabled paging, your EAP was right here. And it will stay like right here plus whatever the size of the instruction you're using, let's say maybe 1 byte, maybe 2 bytes, I don't even remember, but it will stay here. But the end goal is to run kernel in this 2 gigabyte region, right? So you will soon make a jump changing EAP to make sure that you're running it here. And again, we didn't do that in the homework. And if you were surprised, we said, okay, we're not gonna build this complexity because we just don't feel like running the kernel at 2 gigabytes. It's totally fine to leave the kernel running in the same addresses. It's just that you have to allocate different virtual addresses for the user space. And in our homework, I forgot exactly which number we chose, but let's say 32 megabytes, right? And so the kernel has a region of memory from 0 to 32 megabytes in virtual and physical address space. Like physical, it's hard at this point to say, but because the physical pages will be allocated for the user as well. But the kernel will live in this from 0 to 32 megabytes. And then from 32 to and up, there will be user heap and everything. But x86 doesn't do that. So they say, okay, look, like we're going to reserve the lower 2 gigabytes for the user and the rest for the kernel, right? So essentially every x86 address space will look something like, I'll use green for the user, right? From 0 to 2 GBs. And I will use maybe yellow, if we can see yellow here. Yellow isn't probably, no, it's okay, I guess. Just that I don't see yellow on my screen. So I will use orange. And the upper 2 gigs is for the kernel, right? And the kernel will be sitting from, this is 2 GBs plus 1 MB up to the 2 GBs plus the end symbol of the kernel, right? So this is where the kernel will be sitting. The actual kernel, when I say kernel, I say it's data, text, BSS, stuff like that, right? Okay, so this is clear, right? So we did it. And at some point, we're running our instruction pointer. When we jump to main, instruction pointer is currently pointing to let's say main, which is compiled to be somewhere around about the 2 gigabytes plus 1 megabyte question.
I guess.
Good question. I don't know the answer. I don't even I looked at POSIX, but I wasn't really ever a big fan because I never had to do a real POSIX compliant operating system. That's a great question. Maybe POSIX dictates something like that. But I don't know. You should look it up.
That's EIP, right? Main EIP.
Yeah, main EIP.
Sorry, I missed the point. You said when is you said
when are we jumping?
Yeah.
No, remember it was still in assembly and you did something like you enable paging, and then instead of doing call main, if you just simply generate this call main, then it will generate a relative jump, just because that's how assembler works. So that's why we essentially, instead of doing this, we moved main into some, let's say, EAX register or something like that. And then we did call of EAX, right? Just to make sure that it's an absolute call, right, to a specific address.
What's the difference between this and call main EIP?
Well, this is assembler is a language, right? When you write something in assembler like this, it generates a relative call, which will be a jump plus 1000, for example, right? Okay. But that's wrong because we don't want to jump plus 1000. We really want to jump to something like 0x800, or let's say that's 0 will probably not be there, but some address here, right? So X, and then A, B, C, D, right? And in order to generate assembly instruction, which in this format, you really need to use an explicit register. So it will be a jump to EAX, and EAX will contain this value.
So through the EAX, we can jump to absolute JAS, but if we use the call main, it will jump to relative JAS, right?
Correct. Okay, so this is how the story goes, right? So we ended up in main, and I have to stay on track. So inside main, essentially, we said, okay, forget about this first page table because it's very limiting. It only has 2 entries, right? First of all, we don't really even need this entry, right? Because we will never run here again. And we don't really need this entry either, right? So because it just maps 4 megabytes, but maybe we want to map everything up to fizstop, right? And what we are doing here is that we first construct a new page table in a kernel, right? And this new page table will essentially, it will be a page table which will be used by this boot CPU, right? So essentially, we're still running on one CPU. And the address space where we are constructing will contain only this orange part, right? And it will contain, well, it will contain everything mapped from address in physical addresses. Let me use gray here. So if this is your physical memory, right? We will map everything from 0 to fistop. Remember that we like mapping this one as read-write, mapping kernel text as read-only, mapping the rest of it as read-write here, and we're also mapping the higher BIOS region. And we've seen this, that you also had to map this parts of this BIOS region. We're enabling interrupts in a homework, right? So local advanced programmable interrupt controller, and I think and the other, I forget which, yeah, which one?
Yes.
So this is the local advanced programmable interrupt, and yeah, an IOPAC. So you needed to map, instead of mapping all of those pages like x86 does, in the homework, we just mapped 2 pages, just to essentially, that's sufficient to configure those controllers, because when you write into those pages in practice, it doesn't go to memory. It just somehow magically translated by the hardware and really goes to a chip on the motherboard, which implements those LAPIC. I mean, this is really part of the main CPU at this point, and IO APIC, right? So this is the 2 controllers which we were configuring to just enable delivery of interrupts, right? I just wanted to make sure that we understand why this region is mapped, right? So in a homework, we had to do the same, right? And so essentially x86 creates a new page table, this one, which maps everything with a 2 GB shift, right? So this is 2 GBs. This is a fistop with a 2 GB shift. And this one is mapped actually 1-to-1, right? So, right. Just because it's convenient. So you can map it. No, it's probably just makes sense, to be honest, right? So, and after that, we have this page table, right? We load it in the page, in the whatever, like, if we still remember how it works, we load it in the CR3, and essentially we will never use, well, we will use the boot time page table only when we will enable other CPUs. But after that, we're running. Let's just for a second believe that we're running this new page table.
What's the BIOS? What's that?
It's maybe I'm like a little, when I say BIOS, that's probably a better name is to say IO region or something like that.
It's kind of like hardware region map to the memory.
Yeah, it's called memory mapped IO. So essentially, when you write into those addresses or read from those addresses, your reads and writes reach real hardware. And each hardware will have a specific protocol saying, if you write into this address, I will do something, like I will start delivering interrupts, right? And there are two BIOS regions. So one is sitting here right below the first megabyte. But they ran out of, this is where the frame buffer is sitting, right? When we were doing hello world, this is where we're writing hello, right? In one of those, like, it's not all of it, but some subset of it is a frame buffer. Some of it was used by other devices, but eventually they ran out of space in this region. And they said, okay, we need another one, just hardware manufacturers. And they came up with a new one.
So in our homework, we implement this mapping.
Yeah, so you mapped only 2 pages. It was sufficient for the purposes of the homework. It's just wanted to make it simple.
So actually at this time, we already drop off the first region instead, right? You said the first region is also used for BIOS.
Well, x86, in order to print something on a screen, when you really, like, x86 has 2 device drivers, very similar to your homeworks. One prints on a real, like, VGA screen, and another one prints on a serial line. Serial line means that if you're in a data center, those machines will have serial ports, which typically are converted to like serial ports over the network. But again, like when I was young, and even here in the lab, I think we ended up sometimes connected a real serial cable to just read. It just follows a protocol, like essentially sends a letter over the cable, right? According to some specific protocol. But so x86, essentially, when it wants to put something on a VGA screen, it will also use this frame buffer, FB here, and it will be printing H here if you want to print hello. That will be here, right? And In practice, if it's a virtual address, it reaches this physical address, and this goes to hardware, which is the VGA frame buffer. And of course, like you ask a question, like how do real graphic cards work? I mean, it's a similar idea, just that they dynamically configure a region of memory, which will be like read by the more powerful hardware, and those regions will be larger as well. Any questions? Okay, it's okay. But what I'm trying to get to really is the following. So at some point we ended up with main, right? And we execute inside main. Remember, we create a very first process inside main, right? So user init. This user init essentially, like x86 will have a list of processes in a system. It's an array, right? So each of this is a proc data structure, right? And user init essentially allocates one of those entries in the array, very similar to the homework which we're working on right now. This the process will create its own page table, right? And this page table will have an address space which will look specifically like this. It will have only one page mapped in the user area, and it will have like all the kernel address space is mapped according to the rule of the kernel, right? And this thing specifically just does nothing besides invoking an int64 with the goal to exec, right? Because it says I want to exec into a user program which is called init, right? And that's it. And if I ask you a question, so this init code, which we've seen, which was written in assembly, where does it come from? Remember? No. Do you remember? It's not sitting in a file. Where do we get it from? It's very similar to the homework. No, it does look like an L file. Actually, in case of the init code, it's actually just a binary code, like just a tiny sequence of assembly instructions. But it can be an L file, but where is it? Who remembers?
Remember the assembly?
It's okay. If I ask you differently, so the homework is due tomorrow, right? So where is this user code sitting in your Hello World kernel? x86 does the same. Exactly. And so x86 did the same. So x86 for the simplicity reasons, so they say, look, this init code will be compiled as part of the kernel, and it will have this like init code, whatever, init binary, start label, and whatever init binary size, right? It's just a trick. You say like, I want to embed another executable inside current executable. It's not strictly required. As you say, you can go to the file system, but then you have to read it from the file system, which would be possibly totally fine, but they didn't make this design choice. Then they said, okay, like, and in the homework, we don't make this design choice. Why? Because we simply don't have a file system, right? So, and I'm like, okay, if you want to read something from a disk, you have to build a file system, but this is easier, right? And in many practical senses, like, this is just fine. You say, again, my story, like, imagine you have a startup, you have to deliver in a week. It has to show something on your wristwatch, and it has to have like a flashy user level, but that's it. So instead of building a file system, you say like, let's skip it for today. There will be no file system. So no one will ever notice that we don't have any data which we can save on file, but it will load this way and it will run, right? We'll be able to show the demo. No, like, hold on. This this tiny green section, which is showing here, this literally will have some instructions, and it will have instruction int 64, and it will have like a tiny data string, which will have init. And so essentially when you execute exec will go to the file system faithfully and read from the file system and stuff like that, right? But they didn't. They just like this time. Correct, yeah. And in fact, it's compiled in such a manner, it's not even an ELF. It's compiled to run at address 0, and you immediately jump to it, right? So it's all the in our homework, because I wanted you to see that you really you can load a real ELF file. It doesn't have to be like some strict binary. It has like, then I said, okay, we're gonna load an ELF. So in our case, instead of like, in case of a homework, instead of having those instructions, it's really an ELF file with an ELF header, a pointer to the program what segment table, and then this will like point you to like real text and data, right? That's what we're doing, but just slightly different setup. You can go either way. I just wanted to make sure. Any questions about this? Yeah.
First is who write this small program? The second question is that it's not easy.
So is what?
It's after the entry and before the 4 megabytes. Now there. What's the relationship?
You mean like this physically, this assembly code is placed inside the kernel, right? This is location and physical memory, right? In virtual memory, it will be obviously remapped somewhere here and here originally, right? When we give up this page table, it will be remapped somewhere here, right? But it's virtual address. So when we create this address space with the user in it, we just simply, like, if it was mapped here, physically, it was obviously sitting somewhere here in a lower physical addresses, right? So maybe let's change the color here just to be consistent. So gray is physical. We simply allocate yet another page, right? From a memory allocator, we map this page here, right?
Why?
Why? Because the code, okay, so that's a great question. So why? So really, why? Why are we doing this? Why don't we just jump to this? Why don't we just jump to this address? Because we know that the assembly instructions are here. It will invoke int 64, right? Why do we like map it there? Correct, because when we're doing something like move of the init string, and we like remember we have to. That's one great answer. So actually, everyone follows. So because this int64 invokes a syscall, and system calls have to follow a specific calling convention. So they expect the arguments. The kernel, when you reach the system call, expects the arguments to be on the stack, right? And this is like, again, like it's like, so essentially you need to place them, those 2 pointers to string, this one, for example, init string on a stack, right? And the stack itself, if you ask me a question, so it will be actually allocated in the same page upper addresses, why not, right? But you're right, so we have to, when you move this address, in order for it to be correct, it has to be mapped at address 0, right? That's one answer. But imagine we somehow came up with position independent code and we somehow resolve the address on the fly. Does it solve our problem? Can we just still jump to this entry point? Sorry, this one. Can we? What can go wrong? It's a tricky question. It was asked on the exams actually in the past. Shows, yeah. Well, since it was part of the kernel, then yes, it was mapped, right? Doesn't look like to me because the whole kernel is mapped. So this one is also mapped then. Why? Well, hold on. So that's, I mean, when you invoke this int instruction, right, it follows the regular interrupt transition. So it will, remember how the transition happens inside the IDT, if this is the interrupt descriptor table, this entry 64 will choose you a code segment. Sorry, I have some minor spelling problem. Spelling everything backward, CS, right? And this will actually point you to the global descriptor table, GDT, right? And it will choose the, this we don't change, right? So it will point to the kernel code. So it seems to be correct, more or less. It will be in the same, we'll run with the same privilege. We'll do the switch, right? What will go wrong? Something will go wrong. It's a tricky question. So what will go wrong is that, remember that when you transition from privilege level 3 to privilege level 0 with an interrupt, or when you transition from 0 to 0, the layout of the stack is slightly different. We are not pushing two registers. In fact, we're not saving CS and what else? No, we are actually saving CS. We are not saving stack pointer, and we are not saving stack segment. So, which means that the trap frame will have a different layout, right? Which means that when you try to fetch arguments from inside the system call, you will just miss them by two 4-byte values, right? That's why x86 cannot really execute int64 from inside the kernel with privilege level 3, right? That's why we actually map this init code inside the user and will exit into the user level and then invoke exec for the whole machinery to work. That's one reason, right? To answer your question, why are we doing this? Good.
So the first reason also clear. You said the stack. What's wrong when we cannot? What's wrong with the stack reason we have to map to the beginning?
Say this again.
You said the first reason. The first reason is use the arguments, and so we need the stack. So why with the stack we have to use the first, or we duplicate this?
Okay, let me probably take it offline because I don't think it gets into the weeds. It's a nice question. I will send you the answer, or you come and talk to me during at a high level, when you fetch the arguments, if this is your kernel stack, or when you have this functions arg, int, arg, str, and they assume a specific stack layout. They assume that you will have a user pointer ESP pointing to the user stack, right? And I think if you stay in the same privilege level, you will stay on the same stack, and this layout breaks. Essentially, you will not read the arguments correctly. That's why if you want to invoke a system call, you really have to exit and do the invocation from user level. Although you can imagine that you can fix those problems if you really want, but I wouldn't do this.
Seems to me these two reasons are both to be unified, right? User level, like a system call stuff, to be kind of to make the same stuff. Yeah, that's my understanding. Thank you.
Okay, let's keep going because we'll stuck on this forever. But anyway, so the point is that we created this init process, but it really never really runs. It just sits here, right, in a process queue with this page table, with the init code mapped here, and we figured out that it comes from another location in a kernel from here, right, which implements. If you want to think of it, we can say that, well, it's a very, very naive implementation of a in-memory file system. It has only one file which is labeled with this init boot init code labels, right? But what I wanted to get to is that when you finish main, at the very end of main, you enter the scheduler, right? And the scheduler function, essentially, up until now, you were still executing on this, let's call it a boot thread, which was originally like kind of like inherited from the bootloader, from BIOS and the bootloader. And the scheduler essentially implements an infinite loop, which looks at the process table, right? And at this time, when we just reach this point, there is only one process which is sitting here in this process table. This is this user init, right? And what it will try to do at this point, it will try to essentially switch using this switch function, which we covered as part of the context switch, to essentially say, look, I will try to run this user process. I will try to exit into the user level with the switch function, and we'll start executing at user level, right? Is this idea clear that you like to be like you were sitting here on your kernel stack, which you created during the boot time, and this stack will always remain for the scheduler on this CPU, right? When you switch here, so this entry in this process table will have two important things. It will have a page table to which we're going to switch, and it will also have its own kernel stack, right? It's important to understand that each process will have its own kernel stack, right? So what do we have on this kernel stack? Is it empty? Correct. So it has the entire trap frame here, trap frame at the very top, and then it will have a context. Context will allow us to implement the switch and start running kind of like, this is when I say a thread of execution. So this is a like T1, but suddenly T1 like kind of like transforms itself into this T2, right? And T1 save its own context on this thread, on this stack, right? So the scheduler will like when this process will be switching back in the future, back to the scheduler will be able to pick up its state from that context, right? But essentially the idea that this T2 can essentially start executing, and do you remember what it executes? This context has a instruction pointer. Where does it point? Do you remember? Right, so it's a function which is forkret in x86 or trapret in our homework, but essentially this is the function which uses this trap frame to exit into the user level, right? That idea is clear, and this is how you essentially eventually end up running the user code in user level through this trapret, right? So, and like you start running in user level, like it's ring 3 here, right? So you like, let me draw another figure here. So you have this address space of the user process, right? Again, it's pretty much empty. It only has a couple of instructions in the first page, right? EAP is pointing to 0, right? Because this is how we compile it. And the stack pointer is pointing to the top of the page, almost top of the page. We just, yeah, no, actually, I think even the stack is empty here. So it's pretty much empty. And it's just one page of 496 bytes, right? And the kernel part is sitting here containing everything, right? So when you start running, when you context switch and you start running this thread, specifically this, the EAP is set to the first instruction of the user init code, right? And essentially, very soon you execute like only like a handful of instructions, let's say 3 or 4, you hit this int 64 instruction, which brings you back to the kernel, right? And you start executing the like vector 64 and all traps and stuff like that. You reach the trap function, and inside the trap, you execute a syscall, which is an exec system call, right? And this exec system call, which receives an argument, something like /init, will replace this address space with the content of the init process, right? That's clear. And after that, you essentially, it's the same entry. Remember that exec does not change the entry. It's the same entry in the proc table, right? It's just that the address space changes, right? And now instead of and the way exec is implemented in x86, it's literally like replaces it. If it was page table number 1, it just allocates a brand new one. And do you remember the reason why we're doing this? Why are we allocating the brand new one instead of like overriding this one?
We still need
Why do we need them?
the exec file.
To do what?
Exec can be filed.
Yeah, because exec can fail, right? So maybe like we start constructing this new address space, started loading parts of the init file here, like data and code sections. We'll create like a guard page here, create a stack page for it. And maybe right when we try to allocate the stack page, we ran out of pages just because we were already running for so long that the system ran out of the pages on a page allocator, right? And at this point, we will have to roll back and return an error in the original process, right? So that's why we're constructing a new address space. And then when we constructed it, we completely deallocate the old one. But the process entry in the table, the file descriptor table stays the same. And this is the implementation of exec, right? Question.
So here, the EIP points to 0. That means implementation has to be 6, right? Not all. This one is different from all.
Right. So this one is x86 knows that it's at 0. And in our homework, we really loaded an L file. So this is not fixed. Can be anything in this L file. Okay, so then when we replace the address space with now we're running an init process. What happens next? Do you remember? Anyone? Well, our goal is to get to shell, to print the command line, trying to ask the user to start inputting some commands, right? The reason I'm kind of telling this story is that, we had a bunch of lectures. This is the way to connect them together. In the end, everything makes sense here. Your end goal, again, is to, if you're running on a screen, you will have to put into some kind of a GUI application, right? So which will probably say, okay, yeah, enter a password, right? But GUI is just yet another program, or maybe a collection of programs, right? In x86 and in many other environments, you say, I just want to put into shell, and shell will be my way to control the system. And this is how it was, right? So we're not yet there. So we don't have a shell yet, but we're close. Correct. So, and this is specifically this init process. So init process will say, look, I'm going to fork, which will create an exact copy of the init process, right? And then this fork will exec into shell. And I forgot exactly the path, but let's write it like this, right? And so at this point, when you reach this command prompt, how many processes are running in the x86 system? How many entries in the process table are allocated and active?
The number of CPUs plus NDs and plus shell.
Almost. So when we did the fork, we created another process, which is a copy of init. So it will be an init. And I will quickly draw it right here. So this one was number 1. It's still number 1 because this init came from the same user init, right? This one is number 2. And this number 2 essentially exec itself right, into the shell. So this init becomes shell, right? But we still have two. So it's only two, right? If we have a system on with multiple CPUs, are they running? Where are they running? On which CPU they are running? We booted on one, right? And at some point, remember, I was explaining that you send those magical interrupts to other CPUs, and you send it like, if this one's CPU 0, this one was CPU 1, you ended up running something what is called MP entry, and then this one was running MP main, and this one is also entering the scheduler function, and this one is this infinite loop, and this one is running an infinite loop. And this is the process table. You have two entries. One is for init, and this one is for shell, right? So where are those two running? Both on 0, so that's one version. Anyone else? Uh-huh. Mm-hmm. Like, this is a process array, right? It's a global variable. Just for everyone else, I understand that it's a little hard to follow, but again, the global variables will be sitting somewhere here in a kernel in the data section, right? Agree? And so this is globally accessible from all the CPUs, right? So then how will it fly? So literally, remember when we enter the scheduling loop, we're acquiring a lock here, which means that a timer interrupt arrives on another CPU. By the way, you disable timer interrupts, but you disable interrupts on only one CPU locally, right? So other CPUs can receive interrupts. You get here and you're trying to acquire the lock, but you cannot, right? So you will be sitting here. And this guy, for example, says, okay, I'm gonna go through the entries of this process table and I pick whatever the next for me. And I, let's say, will run shell for a while, right? I will context switch to shell. So the shell will be running on this CPU. It does unlock here, right? And like switches to shell. Meanwhile, this guy received this lock. It also looks at the table. Maybe it also looks at this shell process, but it's already running, so it doesn't have to context switch to this, right? And maybe it finds init and say, okay, init is not running yet, so I will pick init and I will switch to init on this CPU 1. So it will do a switch to init, right? And it will run init on this CPU for a while. But you can imagine that this picture will repeat in 10 milliseconds. And they essentially just arrive to different conclusions. So maybe CPU 0 will pick init from a global table, and CPU 1 will pick shell from a global table. So they will be kind of semi-randomly bouncing between the CPU 1 and CPU 0, right? And that's fine. That's how, of course, like Linux will make more sophisticated scheduling decisions. Maybe there will be a policy that this process will run only on this CPU for whatever reason. Like maybe it's a low power core and you pin a process or a thread within a process to a specific core. But x86 doesn't have this policy, and it just picks and randomly moves them around from one CPU to another, right? And that I wanted to make sure that we understand it, that like if shell starts other process, like you start at a pipeline of like 10 different things, like grab, less grab, sort, whatever, they will all be sitting in those entries, right? Like some of them will be waiting on a pipe to read something, right? So they will be in waiting state, but essentially x86 will be picking them in some semi-random order on any of those CPUs and trying to run them, right? That's how it works. And I wanted just to make sure that it's clear to you guys. Question?
So here we'll see the init will like fork process for the shell. So what else the init will do when it will finish?
Yeah, so in x86, init never finishes. So, oh, actually it does if you very carefully read the source code. I think when it runs out of memory and fails to, I mean, we can take a look real quick if we want. So it's not a big deal, to be honest, to take a look at the x86. Let me just zoom in here. And you say init. And this is how you approach this problem. So you say, look, if I suddenly not clear what's going on, you really look at the source code and you will have a better source code tool, right? And x86 is reasonably small to understand what's going on. So this is this infinite loop, this for line, right? So, and does it ever exit from here? Well, it does exit in these two cases, right? So when it failed to fork and PID is negative, right? Or when it failed to exec. At this point, it exits and the whole thing will probably panic at this point. But normally, unless you run out of memory, even if your shell exits, you will be waiting in this line saying, okay, I'm waiting for my child to finish, right? Remember this wait system call, which you used in like when you were implementing shell. And I'll print that I got a zombie, inherited a process maybe. And at this point, you will fork again into a new shell, like fork into yourself and then invoke exec starting a new shell. Right, you can exit this original shell. So because the shell is a generic program, you can start one shell from another recursively, right? Like on Kate, we start bash from TC shell, right? And so you can say exit, it will exit, but x86, again, it's just a design choice. There is nothing really magical about it. You can say, well, you exited the main shell by, so like you decided to shut down the system or something like that, which is a meaningful design decision. So there is like, at this point, you decide what you do. Question?
I'm thinking, even if this presentation like the PID is more than 0, I'm thinking other processes still running.
Correct. Yeah, that's a good question. What happens to those other processes if you somehow exited the shell? Wow. Yeah. Right. So you can like, that's a good point. Maybe that's not a very good design decision, but they did it this way. And it's illustrative enough for everyone to say that, look, we can build it differently. That's one way to build it, but we can probably build it in many different ways. Okay, let me go back to this drawing. So, where is it? Hidden somewhere. Okay, so we got this idea that these processes are running on different CPUs, right? And that's more or less what I wanted to cover today. It took me a little longer, but that's like essentially if you ever come back to this class, so you should watch this lecture and say, okay, I kind of remember how it was working, and now I understand. And every system which you run on your CPU or like on your laptop or Android device, Mac OS, kind of is very similar inside. So they do very similar things. They're much more complicated just because they support a lot more corner cases, like in this, what if the shell exits? So they will have a better answer to this, right? They will probably not. In Linux, I think if you kill the init, you reboot, right? If I remember correctly, like someone who runs Linux can try right now. I would try, but I will lose my lecture right away. I can kill init on Mac, but if you don't, I'm pretty sure like that we will. Okay, man, I'm watching so much interesting things. We shouldn't. This one. I wanted to show you. So if I do this ps minus ax grab for init, yeah, there is like, there must be init. Which one? Should be, no, Mac doesn't have init. System D. Oh, then you know better than me. Yeah, maybe.
I don't know.
No, it's if I do this, so launch D. So that's their init. The process was process ID 1. So if you kill this, we can do it at the very end of the lecture. Let's see what happens. That's a good way to finish, right? I'll do it. But pretty much, I mean, the reason I'm talking about is to convince you that those systems do very similar things. So if you ever have a conceptual question about what happens inside, you can take a look at x86, right? Okay, any questions about this boot thing? Or like not boot, but in general, booting into the kernel and running it. And your homework essentially does very similar thing, and the extra credit assignment asks you to implement like two processes and context switch between them, which is not super hard after you understand everything. Okay, so we still have maybe like 13 minutes, and everyone was probably waiting for specifically this part of the class, but I only got it right now. So this is the midterm from last year. Let's just quickly look through. So I ask questions, look, on calling conventions, which I said, okay, everything will be covered, right? So the first half of the class and the second, although here I ask only one question on a calling convention. Then I ask something on a process, like questions like explain the address space of x86. Actually, super duper easy, right? So again, people will tell me that I'm a mean person, not so mean, and at least like anyone, like I just said, okay, how it looks, right? So data sections, page guard. Then I ask you, this is a question which says, okay, what is the possible outputs of this program, right? So it's like a POSIX style system call interface style question. And then we go into something like, again, back to x86 and how things are running. So this one recursively executes this program, and I asking a question, okay, how many times it will run? Because at some point you will run out of stack. And this is what we just discussed. Alice is running an x86 system. Is it possible for the init process, which is created on the first CPU, to run on the second CPU at some point in time? And be specific, explain, right? So that's what I was just explaining. Init started, but then scheduler picks it up on the other CPU and runs it there, right? So it's not a hard question, but you have to understand what's going on. Some questions about the context switch, like specifically context and proc data structures. One question about the file system. So we haven't spent a lot of time on file systems. So it's like, can you explain what operations x86 file system performs when Bob invokes the following command? ln is a link. Well, we'll see like how many questions they can ask on a file system. But okay, let's solve a couple. Just so since we're on this, let's start with a simple one. So Alice is my guinea pig. So she executes this program. Can you guess what the possible outputs of this program are? And we will do our wonderful poll. Do you still remember the link? A Burtsev. I have a poll here. Otherwise, you know those guys who just left. Oh, wait, activities, wrong. File system recap. Do you know where to go? You know the URL? Okay, good. So how do we... here we have to probably like, okay, I'll put it on a side. So what are the possible outputs? Okay, I will ask you a question. So can you click multiple answers, or it doesn't allow you to click just one? Yuck. You can change it, but simply just one. How can I quickly fix it? Let me fix it real quick. I will hide you. I'll hide the screen for a sec. That's my trick to hide I will edit the activity just to make sure that we can edit multiple. Quickly edit it. So what about now? Can you click multiple? Yes? No? Man, so all this time Custom, it says multiple choice activity. From the web, restrict participants. Oh, how about, really, right now you cannot still click multiple? No, you cannot, right? Okay. Then it's, you can. Okay, cool. Oh, maybe I click save now. Sorry, that's why. Okay, so let's back to the program. Let me exit my slideshow. Exit the slideshow. Back to the text of this. What do we do this? So we can wait. Sorry. Tile. That tile. Roll anywhere? No, cannot tile like that. So then we will do something like this. Yeah, see, look at the program. It's a little funky. It's a little bit more. My problem is that this thing always tries to hide itself. Man, really? Okay, so is it over in a different string? Here. Got it. Where are we? This one is. Where is it? Well, okay, this one. This one got its own screen now. Okay, apologize for this. So now we have them on one screen, and so okay. So what are the possible outputs? So anyone cares to explain what's going on? Okay. Wait, let's pick a different person. So you talked about, like, let's do a volunteer. Okay. Yeah. Mm-hmm. Hold on. I like your story because it illustrates the certain gap in understanding. What does it mean that the parent exits faster? It doesn't prevent the child from running, right?
Yeah, but
so remember my picture like 5 seconds ago. I mean, I get it, like everyone will half asleep. I would too probably. The process queue, right? So we have parent and child in that queue, multiple CPUs. So CPUs can pick parent and child in any order, right? So that's why you say, look, it's either like food prints first or basket prints first, but even if the parent exits, the child is still running. So there is no wait here, nothing like that. In fact, this thing just exits, right? And the child is running. So is it clear that those guys can execute out of order and can finish out of order, but it doesn't prevent exiting the other, like it doesn't mean that the other program exits. Correct. So, and I also wanted to see this case because last year we even were giving like complete grade for like just printing this two out of order, but really this code doesn't check for the fork result. So it can just get a negative PAD, enter line 12, print foo, and exit, right? And that's also a valid sequence, right? Is it clear to you guys? Right. Everyone is good on this? Any questions? So it's not super hard, right? So again, and you were close, but I like that you like kind of missed the last point. And it's very important to understand that those, like the moment you start them, they are largely independent unless they are synchronized. So let me close this activity. Let's look at something. I have a different activity. So since we're on this, so there are these guys, Bob and Alice. Bob says that this output, like essentially the torn output, where one of the child or parent starts printing on the console and another is context switch and starts running, right? And Bob says, okay, will it ever happen? Like, can this output ever happen or not, right? Let me start another activity. What do you think? Will it? Do you understand the question? I mean, I like how to approach this question, how to answer it. Yeah. Like this string which I'm showing is not specific. So maybe I should say FO and BOS, for example. And I forgot what FB, F, start of foo, then BOS, then O, then Z, then O again. So they context switch like 3 times in this example, I think. Almost. So do we see a pipe here? Good question. So what is the write? So where does this write go? Does it go to a pipe or not? It goes to standard output. So what is a standard output? Maybe I didn't spend enough time explaining it, but it goes to, there are some like special type of a file, which is called, it's a device. And in this case, x86 supports, I think, only one type. Device type is a console. And it's very similar to your homework number 3, where you, like, we're printing something on a screen. So we didn't print through a file, right? So it's not really, but x86 uses the same code kind of, but it goes to the special device type and it says, okay, instead of doing a file write, I will do something what is called the console write. And the way to approach this question is to essentially understand where it goes into the system, right? So where it goes in terms of code, right? So you say, like, you say grab for write, just because you say I don't really understand what's happening here at all, right? That's why you have like 2 hours, right? And you say I will first go to the definition of a write, which will take me forever, but somewhere here inside I see that I have a file write, I have something else. So let's grab for file, right? Narrow the search real quick. And file write is called from sysfile. Okay, so we got it. So it's syswrite as a syscall, right? It just fetches the arguments, goes to file write. So clearly we say like something is there in a file write. Let's take a look at a file write. So it says, okay, file is writable. If the file is a pipe, then we do a pipe write. If this is a special file, so this is like if it's a regular inode, we're gonna do the write right into the inode. And do we have anything else? We don't, which kind of sucks, and I don't know the answer myself. But let's go into the write and see what's going on there. So I would imagine that. I would imagine that we will find something meaningful there. So, okay, it says, okay, so here it's a special, it seems that inode can be in a special type. It's not like a file type, it's an inode type. And it seems that it's a device. So, and it says, okay, so there will be a table of these devices. And this table will have a write method. So that's how they implement this polymorphic write. And if we grab for this, which is def as W, let's take a look at what it does. It looks like, for example, here, when console initializes itself, it will have those 2 methods, console write and console read. And at this point, I will skip a little bit, so just for the sake of time, because we're 1 minute over. So, but this is a console write, right? And what kind of conclusion can we make from looking at this code about those torn writes? Correct. Right, but that's the explanation. So you say like in line whatever, you can find it on Google, or like in line get it from the x86 PDF. So really this lock is critical. And we understand why it's critical. So, and you say, like, do a home experiment, just remove this lock and see what will happen. So I think I did. Maybe it's a little less trivial to remove it, but it's maybe not. Just comment out this line, those two lines, 279 and 282. And then most likely we'll get a torn right, because really it loops through the buffer, outputting characters one by one. So you clearly will get a torn right. You might even lose. Yeah, maybe you can lose characters as well, right? Okay, but that's again kind of the flavor of how to answer those questions. So I'll stop here, but I promise I will post the answers to the other questions. Feel free. There is this pin thread on Piazza for the exam thread. Just keep asking questions there. I'll try to be active to just help you. My office hours are kind of like at 11, so today 11 to 12. So feel free to come back. Okay, I'll see you Monday then.
Clearly, not clear about this question.